Hello, I'm here to talk about OH-Picker. It's an experimental program for applying affine transformations to color palettes in lab color space. First, let me introduce myself. My name is Oswald Hurlem. For 2 years, I worked as an independent game developer and game development student. My project was a voxel game, which is either canceled or it's put on hold depending on how you want to look at things. Before that, I worked in cloud and enterprise type of work. I'm currently looking for a new job. This project was done as a personal exercise for me to get some experience quickly making prototypical graphical user interfaces using Dir.im GUI. I wanted to satisfy some curiosity I had regarding the lab color space. The project was also inspired by some difficulties I have in quickly making visuals which are easy on the eyes. And I wanted to improve upon similar products like Adobe Color by offering more power to users. Was I successful at any of these goals? I don't know. But first, let's talk about Lab. OH-Picker uses the lab color space and was designed with it in mind. To understand how to use OH-Picker and why you would want to, you should have some familiarity with it. If you already know about Lab, feel free to skip to a timestamp which I've linked to in the description. So like many subjects, Lab has a really complicated Wikipedia article, but it's a pretty simple concept and you don't need to know a lot about it. In fact, OH-Picker is not the product of an intense study of color spaces or colorimetry, or whatever it's called. I've only done enough research to learn some core ideas and apply them. So Lab is a means of representing colors with 3 numbers, just like with RGB or hue, saturation, and value. In Lab, L represents lightness, ranging from black to white. A represents how green or red a color is, and B represents how blue or yellow the color is. In that sense, it's a little bit like the YUV color space, if you're familiar with that. Most of the time, when Lab is used in a computing environment, L ranges from 0 to 100, and A and B range from negative 127 up to 128. There's a fairly simple conversion from Lab to RGB. One important thing to know about Lab is that a lot of its space is taken up by colors which can't be displayed on an sRGB monitor. And so if you look at the range of displayable colors within the lab space at large, it makes a sort of fat parallelogram shape. So you might think it's a little weird that Lab has as 2 of its axes red versus green and blue versus yellow. This choice is due to how colors are perceived inside of the brain. Although the human eye has photoreceptors to pick up the 3 colors red, green, and blue, those photoreceptors go through a conversion within your nervous system and become a set of 3 different pairs of signals. Your brain then takes those signals for each pair to come up with what colors it sees. This is called the opponent process. The 6 signals that are output by the opponent process are black, white, red, green, blue, and yellow. Once you become aware of the idea that red, green, blue, and yellow can also be their own sort of set of paired primary colors, you start to notice instances of it all over the place. So a few examples of this: Uno cards. A lot of video games will color characters red, blue, yellow, or green. You can see it in the Microsoft Windows. Linguists have found that in languages which don't have names for all of the colors, there is a order that languages tend to develop names for colors as new words are added to their vocabulary. and it usually goes in the order black and white, then red, then yellow and green, and then blue. And then the YUV color space also was sort of designed with this in mind. It basically models human color vision in order to make it so, in order to better enable images to be compressed. And so it also treats red, blue, green, and yellow sort of as a separate primary colors. The quality of lab that is most important is that it attempts to be perceptually uniform. That means that if I start with a color and I increase the L value by 20, I get a color that's as visually distinct from where I started as if I were to increase the A value by 20, or if I were to decrease a value by 20. In this way, it's a lot better than other color spaces like RGB. In fact, I have a little comparison here set up. You can see with this RGB example that even though we're doing hops of 50 units in every direction, the amount of difference between adjacent squares is all over the map. So these two look very close together. These two look very close together compared to these two. Or all four of these look much, much different than gray, even though the step that we're doing is the same for all of them. We're starting at 128, 128, 128, and we're increasing or decreasing a value by 50. RGB is not a perceptually uniform color space. This is because the lab color space was developed using survey results, lots and lots of survey results where they asked people if they could tell apart a given pair of colors. So lab therefore offers a simple way to quantify the distance between any two colors, and that's just by taking the Euclidean distance. That's using the distance formula, plain and simple, and it's called, they call this metric delta E. Now, lab is not a perfect or unbiased model, but it's good enough for most needs. So what is lab used for? Lab is used a lot in visual design. It's used a lot in computer vision. It's used a lot in image and video compression. So it's used in a lot of different fields. However, there are certain things that lab isn't good for. For example, lab doesn't take into account the role that context plays in perceiving color. So everybody knows this illusion where square A and square B look like they're totally different colors, but actually, in terms of the pixels on your screen, they're the same color. There isn't a accommodation in lab for that. Additionally, lab was designed by surveying people who were not colorblind. There's not a quick fix present in lab for making something easily readable by people who are colorblind. Lab does not handle high dynamic range imagery. It does not directly relate to the voltages inside of your monitor. It does not directly relate to the amount of ink emitted by your printer. And it's also not as intuitive as hue, saturation, and value, although I do think it's more intuitive than people give it credit for. Also, there is a version of lab that mimics hue, saturation, and value. I haven't tried it. So let's talk about the program. OH-Picker is a program for changing the color palettes of indexed PNG images. It uses lab color space, and taking advantage of the perceptual uniformity, it treats these colors as points in a Euclidean space. OH-Picker is able to apply Euclidean transformations to sets of colors. So on a 2D plane, a Euclidean transformation is a transformation that acts on a set of points, preserving the distances between each pair of points. Similarly, when we perform a Euclidean transformation in lab space, We can change a set of colors while preserving the perceived differences between each pair of colors. Translation becomes tinting, lightening, or darkening colors. Reflection becomes inverting a particular component of the color. Rotation is the last Euclidean transformation, and it's one of the strangest. One thing it can do is hue shifting, but it can also perform rotations in other planes that, well, what they do is any kind of combination of both hue shifting and also changing the lightness or darkness of colors relative to each other. It's very strange. You may remember earlier in this video I used the term affine transformations to describe what you can do to the colors, and that's because non-Euclidean transformations like skewing and scaling are also supported. In the case of scaling, it's pretty analogous to changing the saturation or contrast of an image. OH Picker uses a scene graph. This is a traditional interface for users to apply transformations to a set of objects. It's commonly seen in 3D editing software such as a game engine's editor. It allows users to record a sequence of transformations applied to an object and revise any part of that sequence at a later time. OH Picker uses the scene graph in an analogous way. I chose this model because there's a growing number of users who are familiar with it. It also is an interesting challenge to program. The scene graph has two types of nodes. The first type is color nodes. Color nodes correspond to a color in the image. The only thing they can hold is a color or a displacement from a starting color. Color nodes can be assigned to be the children of transform nodes. Transform nodes can hold child nodes and apply their transformation to them. These child nodes can be color nodes or other transform nodes. A transform node's transformation is expressed as three different vectors: a position, a rotation, and a scale. In order to make OH Picker analogous to common 3D editing scenarios, we elected to use a left-handed coordinate system with Y corresponding to a color's L value and being represented as the upwards direction. The L value is treated as an up and down axis, the A value is treated as west and east, and the B value is treated as north and south. This means that changing a transform node's yaw rotation causes its child colors to rotate on the A and B plane. This makes them shift in hue, but not in lightness. OH Picker uses a drag and drop interface for users to modify the structure of the scene graph. Many people will be familiar with it. Multiple nodes can be selected by control clicking and dragged and dropped as a group. You can perform other operations on the selected nodes using the buttons at the top of the tree view, or by right-clicking. A drag and drop interface also allows users to change which color nodes correspond to particular slots of the image's palette. The values held by a color or a transform node can be directly modified using Dear GUI dragger objects. Additionally, OH Picker displays all nodes as well as a spectrum of the displayable lab colors in a triplet of orthogonal cutaway views. The first is a top-down view, showing users the A and B values of the nodes. The second is a view from the south, showing the L and A values of the nodes. The third is from the east, showing the L and B values of the nodes. These views can be zoomed and panned using the mouse wheel and the middle mouse button. To change where each view's cutaway slice occurs, you can drag a slider at the bottom. You can also scroll the mouse wheel within this slider to change the size of the slice. Color nodes are displayed as little lifesavers with their color in the middle. Transform nodes are represented by a hand icon which is performing the left hand rule gesture. The thumb points in the A direction of the transform's local space. The index finger points in the L direction, and the middle finger points in the B direction. The fingertips are colored as a reminder. Nodes can be selected here inside of this view and moved around, although this can be a little finicky. If you have a single transform node selected and you right-click, you can change the rotation of the transform node on the particular plane that you're viewing. When you're done editing the image, you can save it as a normal PNG file. The scene graph gets added to the image file as compact metadata. It's available to you next time you open the image in OH Picker. And that's basically all you need to know. So let's look at some of the applications. By grouping objects to colors together in terms of what object they are used on, it's easy to change the color scheme used for particular characters without really quickly, while also preserving differences between each of the individual colors on that object. So here, for example, I'm going to change this bear from a polar bear into a brown bear. I can also change this background to be a late autumn afternoon. You can use this to create palettes or color schemes for any kind of product where you want the visuals to pop but to also be readable. The lab color space allows any kind of modifications to be linear in terms of how much you're changing and how different it looks. Additionally, you can use the transforms to enforce a certain amount of spacing between objects, so that separate objects remain readably distinct from one another. I created this scene as an homage to the game Video Ball, which has tons of vibrant color schemes that look really cool. But it's not just about style. Lab helps ensure that important information is visually communicated to the viewer. Suppose we wanted to modify this map so that the United States was colored differently than Canada, while still keeping a slight difference in the colors between states and provinces. We might be able to do this by changing the scale of the transforms which hold the United States colors and the Canadian province colors. Then, we can position the United States over in the corner of lab color space, which makes it more red. We can decrease the amount of contrast between the Canadian state colors and move it to a corner where the color to make the colors more blue. In pixel art terminology, a ramp is a special kind of gradient made from a few distinct colors that follows a curve. Pixel art often applies different pairs of neighbors in a ramp to create an in-between color. Great pixel artists always try to find creative ramps to fit their needs. Here's a scene that helps them do that. In addition to helping you make palettes, OH Picker is pretty good at helping you examine existing palettes. So for example, here's a 6-bit RGB palette. We can take a look and see what sorts of midtones are missing from it. Here you can see how much more evenly distributed Commodore color palettes were than the ZX Spectrum. Nothing personal. Solarized is a color palette for text editors. It was made with careful attention to each color's lab equivalent. So if I take a look at it in OH Picker, I can see that the background and content colors form a straight line, and that the accent colors form a ring around it. When I recorded this, I was feeling a little mischievous, so I took Solarized and I turned it on its side. One other type of user who may prefer to edit the transform of a palette rather than those individual colors directly is users of creative video games and other types of lightweight creative software. This is a lot more fun than picking colors individually. And because the distance between primary and secondary color is fixed, the user is discouraged from picking something too visually unappealing. I'll finish with some thoughts. I did this project primarily as a personal exercise to develop my own skills in creating graphical user interfaces. I also did it because I was curious if something like this could be useful. If it was a little bit useful for me in a rough state, it could be very useful to a power user using a very refined ideal version of it. I succeeded in the sense that I got practice and I did a valuable experiment and I made something interesting. However, I don't think this is the right interaction model for performing transformations on colors in lab space. Having it work on limited color palettes is too restrictive. It would be better if it worked on images instead. Creating a palette for an image is easy, while doing the opposite is not. On the flip side, having the transformations presented as transform nodes in a graph is probably too broad and too power usery of a solution. Each of these individual operations ought to just be their own GUI window. So suppose you want to translate the colors, you select translate from a menu and you don't get any sort of inputs to rotate the colors, which is something that you don't want. In a similar vein, having these kind of be permanent and stored in a prominent location is probably overkill. It's better to have them be transient dialog boxes, or if they absolutely have to be kept around and made reversible, something much smaller like Photoshop Smart filters or effects on like you see in a video editor is probably a better idea. Finally, if I had to pick one particular aspect of this, like one tiny operation that I think is the most interesting, it's definitely performing rotations in color space, because a lot of the other things have equivalents. They are like lightening images, darkening images, increasing contrast, inverting. A lot of those have precedence, but doing the rotations that aren't in the AB plane is definitely the most interesting thing. The general idea of treating lab colors as points in space and applying affine transformations to them works well, I think. It's useful for visual design, and it could be useful for things like animation. Staying within the lab space allows you to have colors transition from one color to another in an appealing way. I can't attest how useful this would be for something that must be physical or photographic. Anecdotally, I found my own lab picker to be better than the lab picker used in Photoshop, and just other color pickers in general. It was much easier to come up with a set of colors that looked nice together. In certain tasks where I had to pick desaturated, more naturalistic colors, like skin tones especially, a real nightmare to pick everywhere else, it was a lot easier. So even though I don't think this program is an outstanding success, it was just an experiment and I was able to make it fairly quickly. So there's that. So I hope you find OH Picker and this video engaging as well.